So let's look at graphing the data. And if we have a look at this here, this is from one of the previous videos on deriving the formulas. We've got here that if we go and rearrange this formula into the equation format of y equals mx plus c, then we'd have r equals sine of 2 theta on g u squared. We can do any of these other ones here, but this one here actually sort of makes sense, I guess, because we want to look at what is the range compared to what is initial velocity. That sort of makes intuitive sense. And I can change that initial velocity there, that it exits from the pipe, by changing the gravitational potential energy. The higher I lift it up, the more gravitational potential energy it has, and therefore the more velocity it has when it leaves that tube. So it sort of makes sense to be able to go and plot r versus u squared. Now we need to make this into a graph where r is on the y-axis and u squared is on the x-axis. So I'm going to go up here and I'm going to go and get the measured value of r. That's this one here. And I'm going to hold down the control button and I'm going to select this column here. Now I've added this column here, which is u squared. And the reason why is because down here it says it needs to be u squared. I'm not plotting r versus u, I'm plotting r versus u squared. So I need to square it up here. So let's insert a graph. Let's go and insert a graph. And there we have it. We've got a graph. Now let's go and start checking it out a little bit. We'll put on here, let's get rid of that for a second. We'll put on here the range of projectile versus the initial launch velocity squared. Okay, now let's check to see if this is actually right. So down the bottom here, we should have on the x-axis, we should have the velocity squared. And you can see that the range in the velocities goes from about 10.2 up to about 30.4. And it has to be on the x-axis. So the x-axis down here, and we notice we've got values from about 0.5 all the way through to about 1.5. So it's quite obvious then that what's actually happening is it's plotted them the other way around. It's plotted the displacement on the x-axis. And we want the displacement, or the range, on the y-axis. So how do we go about fixing this? Well, let's get rid of this for a second and drag that out of the way. And you might know a little bit of Excel where we could select this graph here and then let me see if I can pull the top down. No, you probably won't be able to see what's happening here at the top of my screen, but I'm going to go across to, I think it's design. Yep, design. And straight up above here, I've got switch row or column. And I'm going to click on that. And you'll notice that what it does is something really bizarre. And it's not done what we want it to do. All we really wanted it to do was swap this column's data around with this column's data so that became the x-axis and that was the y-axis. The range was the y-axis. But it didn't do that. It did that instead. So that obviously isn't going to work. So the other thing we can do is we can go and get this data and we can paste it out here. And then we can go and get this data and we can paste it out here. So we put one first and the other one second, but hang on, look what it just did then. And that's because we've got formulas up in here and it's not really copied those formulas over very well. So what we actually need to do is go and fix this up by typing in the actual data. And I've done that already down here. So I'm going to copy that, I'm going to cut that, and I'm going to paste it up here. So I've put the velocity first and the range second. So now this is going to say this is my x value, and that's my y value. Because remember again, back to this, I want the range to be the y, and I want the u squared to be the x. So I've copied the velocity squared, I've put it first, and the range second. Now if I go and get this data, and I insert a graph, a line graph, oops, and there I end up with my data now, where I've got down the bottom here the range that goes from 1.45 to 0.46 up the side here on the y-axis, and the velocity on the x-axis goes from about 10.2 through to about 30.4. So that looks like it's about right now. So I'm going to change this title now, and we're going to call this title the range of the projectile versus the initial launch velocity. And that initial launch velocity is the velocity squared. So I'll just put the little top hat with the 2 there. Then I'm going to go to design, up the top menu, design, add a chart element, and I'm going to put in here the axis title, the horizontal axis, and the horizontal axis here is going to be the velocity, squared. The velocity squared, and then I'm going to add, again, go to design, add a chart element, and the axis title, vertical, and I'm going to put in here that the vertical is the range. The range of, now let's just put the range in meters. And the range in meters. And you'll notice it's not quite a straight line. It's reasonably close, but it's not quite. So the gradient of this line, looking at this here, the gradient of this line should be sine of 2 theta on g. So if you can calculate the gradient of this line, it should be sine of 2 theta on g. And you can notice here that the gradient changes. So you could calculate the gradient here, or the gradient here, or the gradient here, or the gradient here. And any of those points should be sine of 2 theta on g, but because the gradient changes, obviously it's not going to be completely accurate. So what I could do instead is I could right click on here, add a trend line, and we know that it needs to be linear, so I'm going to leave it as linear, and I'm going to put the equation on the chart. And this is my equation. I'll just make that a bit bigger so we can see it a bit better. And we've said before that the y is actually the range. So the range in meters is equal to 0.0491 multiplied by x, which is a velocity, the velocity squared, insert, let's go and make that a subscript, the velocity, superscript, the velocity squared plus 0.0108. Now, we know that it should travel straight through 0, 0, because if you have no velocity, you will have no range. So it should pass through 0, 0 at the origin, and it doesn't. There's a little bit of uncertainty here already. And later on, when we do a bit of analysis, we can actually calculate the uncertainty in the gradient. But for now, let's just leave it as that. I'll move that over here a little bit. I'm going to change the color of that font. Make it red. I'll make it a little bit smaller so it fits on the graph a bit better now that we can read it. And that's your gradient. Sorry, that is the equation for the line of best fit that we just placed onto that graph. So what can we do with this? Well, this over here, the 0.0491, is the gradient of this line of best fit. And how accurate is our data? Well, I guess what you could do is compare it to what it should be. So if we look over here, the gradient should be the sine of 2 theta on g. And this is a data table for an angle of theta of 45 degrees. So it'll be sine of 2 times 45 over g, which is the sine of 90 on g. So if we get a calculator on screen and we say, okay, the sine of 90, so 90, and this calculator works backwards, a sine of 90 is 1, divided by g, which is 9.81, is equal to 0.1019. Let me take a screenshot of that. That's what the gradient should be. Using the formula, that's what the gradient should be. What do we get as a gradient? We didn't quite get that. We got 0.0491, and it should be 0.101. Given this formula, that's what it should be, and this is what we actually got. So we could work out the uncertainty in that as well as a percent error. Given a velocity, we should be able to work out the range and have a gradient of that as opposed to that. So let's get this graph then now, and let's do something with it, shall we? We'll grab that graph out, I'm going to copy it and I'm going to put it into Word, and let's do up an analysis. Let's do an analysis of this graph. All right, I'll just remove that part of it for now. Actually, let's cut that out, and I'm going to put that, no, I'm not. I'll put that there for the moment, just so that we have it on the side. And let's type up a bit of an analysis, I guess, of this graph. So when we analyze something, what are we required to do? Well, I've copied in the analysis of evidence criteria, and it says appropriate application of algorithms, visual and graphical representations of data about gravity and motion, well in this case it's gravity, and forget about electromagnetism, by correct and relevant processing of data. So if you in Excel, when it did all this processing of data, so you calculated all of these things in here with the correct formulas, and then you went and selected the right one, of the correct formula here, and then you went and selected, which variable to go and put against which variable correctly on the axes, then you would be doing this bit here, where you've appropriate application of algorithms. You've done the right algorithms. You've visually and graphically represented the data. Now, we haven't done all of that yet because we need to do some more stuff on error analysis, but we're starting to. Correct and relevant processing of the data. Systematic and effective analysis of experimental evidence about gravity. Demonstrated by thorough identification of trends, relevant trends, patterns and relationships, and thorough and appropriate identification of the uncertainty and limitations. We'll do that in the next video. Pardon me. In this video here, we're just going to look at identification of relevant trends, patterns and relationships. So let's go back into here, and the patterns, trends and relationships. Well, let's just do dot points to start with, and we're going to say, to start with, what do we notice here? There is a linear relationship. As the velocity increases, the range of the projectile increases. The relationship should be directly proportional and should pass through the origin. The results do not pass through the origin. The origin. The gradient is 0.0491. There appears to be some leveling. I'll put that in inverted commas. Leveling off of the graph towards the higher velocities. Although more tests may be required at higher velocities. Velocities than was tested here. And this is then converted into a paragraph that says, in graph 1.1, the range was plotted versus initial velocity as per the formula. R equals sine 2 theta on g times u squared. Graph 1.1 shows a positive relationship between the exit velocity of the projectile and the range the projectile travels before landing. It was expected that the relationship would be directly proportional and should travel through the origin, as an object with zero velocity will have zero range. This was not the case, as the y, or the range, intercept was 0.0108. This is a very small inaccuracy that may be accounted for by the imprecise experimenting techniques. The experimental gradient was 0.049, while the theoretical gradient should be 0.0102 using the formula m equals sine of 2 theta on g. And the next video, we will look at accuracy and imprecision.